What do multiples, positive integer roots of 2, Fermat's last theorem, this binary number, and 2314 microseconds have in common? Music. Vocal or instrumental sounds, or both, combined in such a way as to produce beauty of form, harmony, and expression of emotion. In other words, wiggly air that's good. But if wiggly air can in fact be good, how can we formalize that as a theory? How can you invent music? Sound doesn't actually have to be the only thing that's able to be musical. For example, you could think of dance as musical. So let's actually invent musical sound. Let's say that sound is musical when specific sounds are made over time, and those sounds can be different. We can observe then that sounds can be different to each other in loudness, sounds can be louder than each other, and pitch. Sounds can be higher than each other. Loudness varies a lot depending on the distance between the observers of a sound, but pitch doesn't, which makes pitch the best way to tell the difference between sounds. Periodic sounds have the times between them repeated. It follows then that periodic sounds can be evaluated as the quantity or quantities of time between them, and aperiodic sounds can't. For example, periodic sounds could be made every second, 2 and 3 seconds, which would make up a periodic pattern. The quantities of time between the simplest periodic pattern are its period, if we measure it in seconds, or its frequency, if we measure the quantity of sounds per second. Periodic sounds with one sufficiently fast period have a correlation between that period and their pitch. For example, sounds made every 2314 microseconds, 432 times per second, would have a pitch that sounds even better than A. Sounds made more frequently have higher pitch. It follows then that frequency is the simplest way to specify pitch. Now that we can tell the difference between sounds, and given that there is a continuous selection of sounds, we need a reason to select specific sounds. Harmonics are one such reason. Given a frequency, its harmonics are that and every faster frequency which occurs at the same time as every occurrence of that given frequency. The harmonics of a frequency are all its multiples. A frequency is its own first harmonic, and its other multiples are its second harmonic, third harmonic, and so on. For example, a frequency of once per second has a first harmonic of itself, a second harmonic of twice per second, a third harmonic of thrice per second, and so on. For many ways of making sound, including your voice, those sounds are not one pitch, but many. For harmonic ways of making sounds, those pitches are harmonics, and the first harmonic is the loudest. In fact, it has been observed that people think they are hearing the first harmonic when they are hearing only the harmonics from the second harmonic up, but this doesn't necessarily work for everyone, and could only be an effect of lifetime exposure to harmonic sounds. However, there are other reasons to select specific sounds, so we have run into a fork in the road, a selection, a setting. The settings of music. We need settings of music when we make a selection that could have been made in other ways. Let's set harmonicity to yes. We are selecting harmonic sounds over inharmonic ones. It's just as well, because if we'd taken the inharmonic road, we might have run into drummers. We can now select other sounds from the harmonics of a given sound. We can also select other sounds by multiplying our selected pitches by the multipliers between harmonics. For example, the multiplier between the second harmonic and the third harmonic is 3 over 2, because the second harmonic multiplied by 3 over 2 is the third harmonic. Now we have a selection of sounds, we need an instrument that can make them. We could use our voice, but we wouldn't have a physical way of making the multipliers between the pitches the precise multipliers between harmonics, which, for example, a string would facilitate. The simplest instrument could be buttons that make our selection of sounds in some way when pressed. The buttons would be in one direction along a straight line from the button that makes the lowest pitch sound up. However, this instrument could become impractical. For example, the multiplier between the 6th and 7th harmonics is 7 over 6, and the multiplier between the 7th and 8th harmonics is 8 over 7, which have a difference of a little over 2 hundredths. Another example is the multiplier between the third and fourth harmonics, 4 over 3, which when multiplied by itself is 16 over 9, and the multiplier between the fourth and seventh harmonics, 7 over 4, which have a difference of a little under 3/100ths. If you wanted to select pitches using these very close multipliers, the instrument could need so many buttons that it becomes impractical. We need another setting of music. Let's set minimal instrumentation to yes. We are selecting minimal instruments over those that make a large selection or in fact a continuous selection of sounds. Perhaps the weirdest setting of music we need is pitch equivalency. Pitch equivalency is the idea that pitches can be equivalent if they have a specific multiplier between them. It follows then that instruments that make higher and lower selections of pitch can make equivalent sounds. For example, the female and male voices have higher and lower selections of pitch, but pitch equivalency facilitates them singing equivalent sounds. There are reasons to think that hearing pitch equivalency is an effect of our biology, but there are also reasons to think that hearing pitch equivalency is only an effect of our environment. Either way, it's a weird idea. However, we are setting pitch equivalency to yes. We need another setting of music for the multiplier between pitches that makes them equivalent. We are setting equivalency multiplier to 2. Now, any sequence of pitches has an equivalent sequence. Given a pitch, the multiplier between it and any other pitch can be used with any equivalent. For example, the pitch F has the non-equivalent 3 over 2F, so its equivalent 2F has a non-equivalent with that multiplier, 3 over 2, which when multiplied by 2F equals 3F. If a non-equivalent pitch is higher than the next equivalent of that given pitch, it can be divided by 2 until it is between that given pitch and the next equivalent of that given pitch. For example, the pitch F has a non-equivalent 5F, which when divided by 2 twice has an equivalent 5 over 4F, which is between F and its next equivalent 2F. It follows then that to select specific sounds we need a sequence of multipliers from 1 that never reaches 2, because that is the first pitch in the next equivalent sequence. We could select multipliers from between harmonics, or we need another setting of music. Let's set equidistance to yes. We are selecting a specific multiplier between all the pitches in our sequence, which make them equidistant. Our multiplier needs to be some positive integer root of 2, because when we multiply it by itself, it eventually needs to be 2. For example, the third root of 2 equals 2 to the power of a third, which when multiplied by itself is 2 to the power of 2/3, which when multiplied by itself again is 2. This integer is the quantity of pitches in our sequence. We need to select a sequence of pitches that have multipliers from between harmonics. All integer roots of 2 are irrational? That's awkward. Finding multipliers from between harmonics in our sequence could be difficult, because irrational numbers cannot be an integer divided by another integer, which is what all the multipliers between harmonics are. But why are all integer roots of 2 irrational? Let's use Fermat's last theorem. Let's say the nth root of 2 is rational. The nth root of 2 equals a over b, where a and b are non-zero integers with the same sign because the roots are positive by definition. If we selected the square root of 2 as our multiplier, we would only have 2 pitches in our sequence, so let's say n is an integer greater than 2. Let's raise the nth root of 2 and a over b to the power of n. 2 equals a to the power of n over b to the power of n. Now, let's multiply 2 and a to the power of n over b to the power of n by b to the power of n. 2b to the power of n equals a to the power of n. Let's express 2b to the power of n as b to the power of n plus b to the power of n. Now we have the equation from Fermat's last theorem. A to the power of n equals b to the power of n plus c to the power of n, where a, b and c are positive integers and n is an integer greater than 2. Fermat wrote that he had proven this equation has no solutions in 1637, but we don't know if his proof was correct. However, in 1995, 358 years later, it was proven. Now, we need to select a sequence of pitches with multipliers that are close to specific multipliers from between harmonics. The multiplier between the second and third harmonics is 3 over 2 equals 1.5. Let's find multipliers close to this. The sequences of 12, 17, 19, and 22 pitches have the closest multipliers to 1.5. What about the multiplier between the third and fourth harmonics? 4 over 3 equals 1.3 recurring. They all have close multipliers. What about the multiplier between the third and fifth harmonics? 5 over 3 equals 1.6 recurring. Again, they all have close multipliers. What about the multiplier between the fourth and fifth harmonics? 5 over 4 equals 1.25. Again, they all have close multipliers. We need another setting of music. Let's set sequence length to 12. Now we need to be able to find equivalent pitches on our instrument. The simplest way is to have two kinds of button in a pattern that repeats every 12 buttons, so every equivalent sequence of our 12 pitches and each pitch in those sequences can be found. It is also simplest to have no consecutive buttons of the same kind. Let's use binary to represent the two kinds of buttons. 0, 1 is the only pattern we can use, but it only repeats every 2 buttons. Let's have one consecutive. 0, 0, 1 is the simplest pattern, but we can also have 0, 1, 0, 0, 1, 0, 1, 0, 1, 0, 0, 1, and so on. All these patterns only repeat at an odd number of buttons. Let's have two consecutives of the same kind. 0, 0, 1, 0, 0, 1 is the simplest pattern, but we can also have 0, 1, 0, 0, 1, 0, 0, 1, 0, 1, 0, 1, 0, 0, 1, 0, 0, 1, and 0, 1, 0, 1, 0, 1, 0, 0, 1, 0, 0, 1. Now we have a pattern that repeats every 12 buttons, but it has 3 consecutive 0, 1s and 2 consecutive 0, 0, 1s. A pattern made up of less consecutive patterns would make it simpler to find buttons within each repeat. There is one such pattern, the one other pattern that repeats every 12 buttons. 0, 1, 0, 1, 0, 0, 1, 0, 1, 0, 0, 1. And that's it. That's music. All of it. That pattern is the pattern of keys on a keyboard. Pressing all the 1s would make up the pentatonic scale, and pressing all the 0s would make up the major scale. In fact, pressing all the 0s of the other pattern that repeats every 12 buttons would make up the melodic minor scale, and the keyboard would look like this. But we had to select so many specific settings of music to make the keyboard. What if we had even made only one different selection? What then? Now you've invented music, other things you need to invent include Stevie Wonder, Adam Neely, and of course, Mundy and Tobacco. If you can do that, you're set.